Hello everybody, this is video 15.4 on summarizing, describing, and comparing data distributions. So hopefully before this you've had a chance to watch video 15.3 where we talked about the center of a data set and we looked at the different ways of measuring the center of a data set. So now we're going to be looking more at the shape of the data set and how widely spread it is. So we're going to be moving away from just the center to pretty much everything else and describing what the data set is going to look like. So let's get started. So the data distribution, the loose definition that we're going to use here is that we're talking about the shape of the distribution. Now, we talked about measures of center before, and there are measures of spread that we can use as well. I'm going to warn you that if you read the book, there are some measures of spread that are used in the book that we're not going to really talk about that much in class. If you've taken a statistics class before, you've probably learned about standard deviation or variance or things like that that are a little bit more computational. We're not going to do that in this class, mostly because some of the computations are going to be sort of beyond what a lot of K6 students are going to be able to do. I know that there is an argument to say that students would be able to put the numbers into like Excel or a statistics program and get the standard deviation out and get the value without having to do the actual calculation. Um, I don't know how much merit there is in just generating a number like that, and that's probably a conversation for another time. So just be aware that there are other measures of spread that we could use, that people do use, that other instructors might use in this class, but we're just not going to talk about it in this class. So I want to give us really sort of a surface overview of talking about data distribution and look at one way of describing the shape that most kiddos should be able to do. So one that you should be able to use in your class with your students. One thing we need to talk about is the shape as far as the way that the tail goes. And if you look at these two graphs, you can see that one side kind of like slopes down. And in my mind, I always think of this like the tail on a brontosaurus. Like when you think about what a brontosaurus typically looks like, the tiny little head, and then it goes big body, and then kind of comes back down to the little tiny tail. So brontosaurus looks kind of symmetrical in that weird kind of way. And so you can see here that you have one side that has a lot more slope down to it. So even though they both have a tail, because they're both kind of trailing off a little bit. So you can see here, this is coming down, but this is coming down a lot more. There's a lot more of this than there is to this. So if we look at where this mode would be, we have a lot more to the left of the mode than we do the right of the mode. And we can tell it's the mode because it's that peak, it's that top point. So even though you could certainly argue that this is a tail also, uh, this is generally what we think of as the tail, the longer part that's going uh, down towards zero. So we refer to this as skewed to the left because the tail, the longer part, is going to the left. And this would be skewed to the right or right skewed. We're not really going to talk about positive or negative skewness as much, so we're not really going to use those terms. Know that sometimes people use them and they're synonymous with what we're doing. But really, when we're just going to be talking about this as far as skewed to the right or skewed to the left. And what that means is just the tail is going to the right or the left. So another pretty common shape that you're going to see is what we call a bimodal distribution. And what bimodal distribution means is, well, bimodal. So we have effectively two modes in our distribution. Now, this is a little confusing sometimes and almost maybe even a misnomer because you can see clearly this is one mode right here. And really, this would be the mode of the whole distribution, the whole thing. because we can see it has the highest frequency here. We can see that it's about 100 students, um, where this point is at the top. But what about this? I mean, is this really mode 2 if these other points over here to the right have a higher frequency than that? Well, that's why I wanted to use this picture, because I think it really shows what's going on. What is often happening in a bimodal distribution is that you have two distributions that are sort of put on top of each other. So to give you an example, let's suppose that in your school you were going to collect the data on the height of students in kindergarten and 5th grade. And we're going to take all those heights and put them together. Well, this height over here, this taller height, would probably be your 5th grade students. And this would be the height on your kindergarten students. And you wouldn't have a whole lot of heights in the middle. Now, you might get some kindergartners that are as tall as a 5th grader. You might get some 5th graders that are as tall as a kindergartner. So you might get some data points here in the middle. But what's more likely is that these two distributions are going to overlap and start to fill in. You may not have anybody necessarily right in the middle, but you might. And so you're going to have really kind of two curves that sit on top of each other. But because you've collected all that data together, you don't see two curves, you just kind of see one curve. But you do see the bulk of the kindergarten students here and the bulk of the 5th grade students here, and that creates two modes. So the two modes are really the mode of the 5th grade students and the mode of the kindergarten students. This would not really be a mode of the whole distribution together. It would just be the mode of that one distribution if we took them apart. And it's a little confusing. If you just remember that a bimodal distribution means that there's two peaks, then you won't go too far wrong. But if you want to sort of understand what's really happening there, it's when we have two different distributions kind of like shoved together like that. If we did the heights of 4th grade and 5th grade, those two peaks would probably come a little bit closer together because those students would be a lot closer in age, and we might not even see a bimodal distribution. The reason why I picked kindergarten and 5th grade is because the difference in height is going to be a lot greater. It's going to be a lot easier to see that as two distributions. So a symmetric distribution, it's exactly what it sounds like. It is symmetric. So there's a tail to the right and a tail to the left, and they're about the same. This is my brontosaurus that I think of. This is the head, the body, the tail, and a nice, even, symmetric distribution. One of the nice things about a symmetric distribution is that the mean, median, and mode are all equal in a symmetric distribution. So you can see that the balance point would be right in the middle. This would be your balance point. And because it's symmetrical, we can tell that the balance would be right in the middle because it's the same on the left and the right. We can also tell that it's the median because if it is symmetrical, that's right in the middle. And we can also tell that it's the mode because it's the tallest point, right in the middle. So your mean, median, and mode are all the same, right in the very middle of a symmetric distribution. A lot of the things that you're going to see and work with as far as data distribution goes are going to be symmetric distribution when you start looking at like MCA scores. Standardized test scores are usually fit to a curve that looks like this. So it's a pretty common curve to see, but this is a symmetric distribution. So we need to talk about percentiles and quartiles. Now, a percentile, this is not a definition that's given because I felt like the definition was going to get a little bit hairy. So I'm just kind of giving you an example here. The 90th percentile is the value where 90% of the data points are less than that value. So as another example of this, we've already talked about a percentile when we talked about the median. The median would be the same as the 50th percentile because half of the data, 50% of the data, is less than that value. Because remember, the median we found to be right in the very middle. The 10th percentile would mean that 10% of the data is less than that. The 40th percentile means 40% of the data is less than that. Now, we're not going to do an awful lot with recording or finding percentiles. The reason why I wanted to talk about this definition in this class is because it's a term that you hear a lot as a teacher when students get their scores back for their MCAs. They'll probably, or any other standardized test, and when you took the SAT or ACT or anything like that, you may have gotten a score back that was a percentile. And it may have said, your math score was in the 89th percentile. And you may have looked at it and thought, like, okay, so I guess I got an 89%. That's about a B. That's not bad. That's one way to think of it, but it's not really what a percentile is. And what it's really telling you is that 89% of the people that took that test when you took it had a score lower than yours. Or you could think of it the other way, that 11% of the people who took that same test when you took it scored higher than you. So that's what a percentile is, and what it means, and what it represents. Again, we're not going to do an awful lot with that here, but it's a good opportunity to explain something that you're going to see a lot in teaching, and you're going to hear this word used a lot. So it's good to know what it is, and what it means, and maybe even be able to talk with students and or their parents or guardians about what that percentile means. We are going to talk about, though, quartiles, and we're going to find quartiles. And the quartiles are not really called the 25th quartile, like the 25th percentile. They're called the first quartile and the third quartile. And so what we have is our data set. So let me draw here. So here's our data set. So we've got our smallest value here, and then we've got our largest value here. And so right in the very middle, we just said, is our 50th percentile. And you'll sometimes see percentile written as a percent sign and then ILE. So percent IL. That's how it works. And so now the 25th percentile is going to be the midpoint here. So once I know my 50th percentile, which is just my middle, which is my median, then I've got my 25th percentile here and my 75th percentile here. Now, as far as quartiles go, we generally refer to this as our first quartile, our second quartile, our third quartile, and then if you want to think of this as your fourth quartile, you certainly can, and this would really be like our 0th. This would be our 0 quartile. You'll sometimes see this in books written with a subscript like Q1, Q2, Q3, Q4, and Q0. It just means the same thing. I mean, this is a different way of writing first, second, third, fourth quartile. It can be a little confusing because at least 25th percentile lets you know we're talking about 25%. So it says right there what it is. You have to remember that first quartile is 25, second quartile is 50, third quartile is 75. But if you can remember those 4 quarters and a dollar, you can remember this. The second quartile means you got 2 quarters. That's 50 cents or 50%. So you have to remember what these quartiles are. But I mean, if you look at the word, the quartile, quarter. I mean, it 4 quarts to a gallon. It should help you sort of remember what's going on in this problem. So let's look at an example of finding the actual quartiles. We kind of went through a rough sketch of it on the previous slide, but let's go through the actual process. So here's our data set: 1, 11, 15, 19, 20, 24, 28, 34, 37, 47, 50, and 57. So if I go through and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have n equals 12 data points. The size of my data set is 12. So if I go through, I know I'm going to have 2 in the middle. So I'm not going to have a single value that's my median. It's going to be the average or the arithmetic mean of these 2 values in the middle. So I'm going to take this 24 and this 28, divide them by 2, and get a median of 26. So this is my median of 26. Now, these two values, neither one are the median. So they split this data set in half. And so now I've got a lower half of my data set and I've got an upper half of my data set. In the lower half, I'm going to do the same thing. And I'm going to kind of put these in two different colors here so we can think about them separately. So now this lower half that's inside the red parentheses, I'm going to do the median again, just like I did for the whole data set. And so now when I do that, I'll go back to red. I got 1, 11, 15, 19, 20, and 24. Again, there's an even number. So I'm going to take these two in the middle. 15 plus 19 divided by 2, that's 34 divided by 2 is 17. And so there's my lower quartile of 17. And then if I go back to blue up here, same thing, I got 6 elements. I look at the 2 that are here. So 37 and 47, well, they're 10 apart, so the midpoint must be plus 5 or minus 5, so I get 42 that way. If I want to do it the more computational way, I'd add them all up. This is 84 divided by 2 gives me 42, which is what we have here. So we've got a lower quartile, an upper quartile, and a median. It should be pretty easy to remember which one is which. The first quartile is going to be the lower number. The third quartile or upper quartile is going to be the bigger number, and the median should be right in the middle. One thing to remember, though, if this were an odd number of numbers, then the median would be an actual element in the data set. It wouldn't go in the lower half or the upper half. It would sort of be excluded. So if we didn't have, say, this 57, then 24 would now be our median. It would be the value in the middle. It would not go in the upper half or the lower half. And so then the first quartile would be 15 and the upper quartile would be 37. So in that case, it'd be a lot easier to find because we wouldn't have to find it. We wouldn't have to calculate any means. But just remember that if you have an odd number, the median does not go into the upper half or the lower half. Now, once we have all these values, we can draw what's called a box plot or a box and whisker plot. And depending on when you went to school, you may not have learned about this. This is something that's been sort of a more recent introduction into the overall math curriculum. So you may not have seen this before. This might be entirely new to you. You might remember doing it in school. So if you do, cool, but just sort of keep in mind that some people may not. So what we've got are 5 values. We have the smallest value in the data set, which is our minimum. We have our first or lower quartile, which is right there. We have our median, which is right there. We have our upper quartile, which is right there. And we have our maximum value. Now, when we draw this, we're going to make this little box right here from Q1 to Q3. And so this is going to show what we call an interquartile range, which is a kind of a big fancy term there. So if you just want to call it IQR, I totally get it. But all that is the distance from Q1 to Q3. Just how far is it from one quartile to the other? And the whole point of this is that value tells us something about the spread of the data. If I have one data set where the IQR is 10 and one data set where the IQR is 2, I know the data set with the IQR of 10 has a lot more spread to it. And we'll look at some distributions and we'll do some calculations with this in class so we'll get a little bit better idea of what's going on with this. The only thing I kind of don't like about this picture that's here is that this would show a very symmetric distribution. All the distances are the same. So typically when you see these box plots, they'll look more like this. Like this. And so they won't be quite as symmetrical and balanced as the one that's shown in this graphic. And so what we could see from this is, again, this is our median here. This is our median, Q2. This is our first quartile. This is our third quartile. This is my min, and this is my max. And so because this whisker, as it's called, is so long, what that's telling me is that this is the tail of my distribution. I know there's a really long way from the min to the Q1. So let's say this is a value of, I'll put some numbers on this so it makes a little bit more sense. Say this could be 1, this could be 10, 14, 16, 18. So we could see that from the min to Q1, there's a distance of 9. And from Q3 to the maximum, there's only a distance of 2. So I could see how that would make that nice tail swooping down to the left. I would also see that the interquartile range for this would be 6, because from 10 to 16, and that circle kind of hit my tens place there, I didn't mean to do that. From 10 to 16, there we go, we see a range of 6, and that's from Q1 to Q3. You don't use the median in actually calculating the IQR, although you needed to have found the median in order to find Q1 and Q3. This is the only thing we're really going to be doing with calculating anything in terms of range and distribution and spread of a data set. Calculating this and drawing this little graph is certainly something that most K5 students should be able to do, given enough support and guidance. But like I said, we're going to stay away from standard deviations and variance. If you know about those, cool. If you don't know about those, that's cool too. Okay, so what I would like for you to do is your checkpoint problem. We looked at this data set in the previous video and in this video, so this should look very familiar. I would like for you to try to find the quartiles. So first, second, third quartile. The min and the max should be fairly direct. And then draw the box plot or box and whisker plot for this data set. So see if you can do that. If you have any questions about this problem or anything else from the video, by all means, please, as usual, bring those questions to class and we'll get them answered. All right, thanks.